On the forward bulkhead of our vessel, there is a clock that defies every human instinct of rhythm. It does not tick with the frantic pulse of seconds or the steady, comforting march of hours. It is a silent, heavy piece of machinery we have come to call the amnesia clock. Its single obsidian hand moves only when a civilization, back on the blue marble we once called home, crumbles into the dust of history. To look at it is to experience a profound sense of vertigo, for it measures not the passage of our lives, but the extinction of our origins. On this ship, we are the only ones left who remember the names of the cities that the clock has already buried. To understand why this clock exists, and how we came to be drifting among the silent, frozen cathedrals of the interstellar void, we must return to a world that believed time was a universal truth. In the early years of the 20th century, humanity lived under the illusion that a second was a second, whether measured on a mountaintop or in the deepest valley. We believed space was a static stage, an unchanging container through which we moved like actors across a floor. But that comforting reality was about to be dismantled by a man who spent his days sorting through the mechanical dreams of others. In 1905, in the city of Bern, Switzerland, a 26-year-old patent clerk named Albert Einstein sat at a cluttered wooden desk. He was a man of unremarkable standing, a technical expert third class, whose primary duty was to evaluate the feasibility of new inventions. Yet, while he examined patent applications for synchronized clocks and telegraphic triggers, his mind was wandering into a realm where no clock could remain in sync. On one unremarkable afternoon, Einstein boarded a tram and looked back at the famous Zittglogger clock tower that dominated the Bernese skyline. As the tram pulled away, Einstein allowed himself a single radical thought. What if I rode a beam of light? He imagined the tram accelerating faster and faster until it matched the speed of the light rays reflecting off the clock tower's face. In that moment of pure, focused imagination, he realized that if he were travelling at the speed of light, the image of the clock's hands would never reach him. To Einstein, riding that beam, the clock would appear to be frozen in a single, eternal moment. To the people standing on the cobblestones below, time would continue its relentless march. But for the traveller on the light beam, time would effectively cease to exist. This was the birth of special relativity, a discovery that would shatter 3 centuries of scientific certainty. Einstein proposed that the speed of light is not just fast, it is a hard universal constant, a cosmic speed limit of 186,282 miles per second that remains the same for every observer, regardless of their own motion. But for light to remain constant, the universe had to make a terrifying sacrifice. It had to make time and space flexible. This is the scientific idea that serves as the foundation for our journey. Einstein's equations revealed that time is not an absolute stream flowing through the cosmos. Instead, it is a subjective experience that yields to the velocity of the observer. As you move faster through space, your motion through time actually slows down. Your wristwatch, the beating of your heart, and the aging of your cells are all tied to your speed. This effect, known as time dilation, means that the faster we travel toward the stars, the more we outpace the world we left behind. The unsettling implication of this discovery is a feeling of absolute vertigo. It forces us to realize that our wristwatch is not a herald of universal truth, but a subjective illusion. There is no now that the entire universe shares. If you were to board a ship and accelerate to a significant fraction of light speed, you would not just be travelling across distance, you would be unlocked from the timeline of your species. You would arrive at a distant star having aged only a few months, while back on Earth, the friends and family you said goodbye to would have lived out their entire lives and vanished into the soil. Last, this is the price of the stars. Relativity has provided us with a loophole that allows a human lifetime to stretch across light years, but it has turned interstellar exploration into a form of permanent exile. We are out here watching the hand of the amnesia clock move, because Einstein saw the flexibility of time. He showed us that the horizon is reachable, but only if we are willing to surrender every connection to the era that birthed us. Yet, even as we grasped the key to the time lock of the universe, we found ourselves hitting a different, more physical wall. For while Einstein gave us the vision to see the stars, we still had to find a way to move through the void. We had to face the brutal reality of the machines we had built, and the ancient, fiery chemistry that was threatening to keep us permanently quarantined in our own backyard. Einstein gave us the vision to see the stars, but it was a self-taught Russian schoolteacher who showed us why we might never reach them. In 1903, in the quiet, frost-bitten town of Kaluga, Konstantin Tsiolkovsky sat in a room filled with hand-drawn diagrams and the heavy silence of his own deafness. He had no government funding, no laboratory, and no peers to debate his findings. He was a man who looked at the sky and saw not just points of light, but destinations. Yet, while the rest of the world was barely learning to lift a heavy-than-air machine off a beach in North Carolina, Tsiolkovsky was at his desk, deriving the mathematical verdict that would define the limits of human ambition for the next century. He wrote down a relationship between mass, velocity, and fire that we now call the rocket equation. It is a simple, elegant formula, but it carries a weight that is almost impossible to reconcile with our dreams of exploration. Tsiolkovsky realized that a rocket is not like a car or a ship. It is a machine that must carry its own energy source with it into the vacuum. But that fuel has mass. To move that mass, you need more fuel. To move that additional fuel, you need even more. This creates a vicious, exponential cycle, a tyranny where the more you want to achieve, the more your own weight conspires to keep you still. To understand the scale of this tyranny, you must look at our greatest achievements as if they were through the eyes of the amnesia clock. Right now, the fastest object we have ever built, the Parker Solar Probe, is screaming through space at over 430,000 miles per hour. At this velocity, you could cross the entire continental United States in under 25 seconds. From the surface of our planet, this feels like an incomprehensible triumph of speed. But on the cosmic map, it is a snail's crawl. At this peak, human velocity, reaching the nearest star, Proxima Centauri, would still take over 6,600 years. If a human life lasts 80 years, travelling at our current maximum speed would carry you across barely more than 1% of the distance to the closest star before your heart beat its final rhythm. You would spend your entire existence in the dark, and your children would spend theirs, and their children's children would still be nowhere near the light of another sun. The numbers are even more disturbing when we measure our progress against the true edge of our home. We often think of the solar system as ending at Pluto, but the sun's gravitational grip extends much further, to a frozen shell of ancient debris called the Oort cloud. At humanity's current maximum speed, reaching just the inner edge of this cloud would require approximately 600 years of continuous travel, an entire human lifetime spent at the pinnacle of our engineering would not even allow you to escape the sun's gravitational family. Measured against the scale of our local neighbourhood, your entire life of travel would accomplish less than crossing from Manhattan to Brooklyn. Consider Voyager 1, the farthest human-made artifact in the void. For nearly half a century, it has been hurtling away from us, covering 15 billion miles, a distance so vast it took nearly 50 years to achieve, Yet, if the journey to our nearest neighbour was a cross-country road trip from New York to Los Angeles, Voyager 1 would have travelled roughly 100 feet in 47 years. You could still see the ship from your driveway. Your neighbours would watch you age from youth to retirement, and your car would remain visible from their kitchen window, a stationary ghost on a map that refuses to move. The reason for this paralysis is the chemical wall Tsiolkovsky discovered. Every rocket we have ever launched operates on the same principle as the first Chinese fireworks 1,000 years ago. Hot gas expelled from one end pushes the vehicle in the opposite direction. But chemical propellants, the combustion of hydrogen and oxygen, have an absolute ceiling. No amount of engineering genius can make a water molecule exit a rocket nozzle faster than the laws of chemistry permit. The energy released by breaking and forming these chemical bonds has an absolute ceiling, and it is this ceiling that turns our stars into unreachable mirages. The mathematics of the rocket equation now presents us with a calculation that is not just a hurdle, but an existential wall. If you wanted to accelerate a small probe, nothing more than a small car weighing 1,000 kilograms, to just 1% of the speed of light using chemical fuel, the amount of propellant you would need is not the mass of a planet or even a star. To reach that 1% mark, you would need a starting fuel mass exceeding the total mass of the entire observable universe. The mass of every galaxy, every star, every atom in the cosmos would not provide enough chemical energy to push a single human-sized payload to even a fraction of the speed of light. This is the tyranny of the rocket equation in its most brutal form. The equation contains an exponential function that punishes any attempt to go faster with a requirement for fuel that quickly exceeds any physically meaningful quantity of matter in existence. It is as if the universe has designed a system of accounting that specifically forbids us from leaving our home. The unsettling implication of Tsiolkovsky's math is that using current fire-based technology, we are permanently quarantined within a microscopic bubble. If we are trapped within 1% of the distance to the nearest star, a region so small that on a galactic scale it is practically zero. We have mastered the art of fire, and we have used it to reach our moon and photograph our planets. But that fire is too cold to carry us across the interstellar desert. When you look at the amnesia clock, you realize that for a chemical civilization, the clock doesn't just measure the fall of empires, it measures our entrapment. We are biological beings bound to a chemistry that is too weak for the distances we wish to cross. The stars are not just far, they are categorically unreachable by the means we currently possess. We are like a species of flightless birds on a tiny island in a vast ocean, looking at the distant shores of a continent we can see but can never touch. This realization reshapes everything we thought we knew about exploration. The problem is not that the stars are far away. It is that the map was never drawn for us. Our brains, evolved to understand the distance of a valley or a day's march, are useless at judging the survival of a 4-light-year void. To our instincts, a rocket feels like a ship. To the universe, it is a microscopic spark that dies before it can even flicker in the dark. We are living in the chemical age, a brief window of history where we have learned to use the energy of molecules to leap off our rock, only to find ourselves hitting a ceiling we cannot break. We are huddling in our own solar system, staring at the amnesia clock, realizing that the fire that brought us here is not enough to take us further. Using the fire of chemical bonds, we are cosmically isolated, trapped in a local pocket of matter that we may never truly leave behind. But Tsiolkovsky, even as he wrote down the equations of our imprisonment, knew that fire was only the beginning. He knew that to break the chemical wall, we would have to look beyond the energy of the molecule and toward the energy of the atom itself. Yet, as we moved from the fire of chemistry to the fire of the stars, we would discover that the universe has even more ways to kill us, and that even our fastest machines are still nothing more than snails crawling across a desert that is expanding faster than we can ever hope to run. We return to the amnesia clock, that silent sentinel on our forward bulkhead. Its hand remains frozen, a mockery of our perceived progress. We have transitioned from the theoretical dreams of Einstein and the chemical equations of Tsiolkovsky into the era of hardware, the era where we have finally truly begun to move. But as we look at the readouts of our most advanced machines, we are forced to confront a reality that is perhaps more terrifying than being stationary. The realization that even at our absolute peak, we are barely more than ghosts haunting a driveway. In the summer of 2018, humanity launched what would become the crown jewel of its engineering prowess, the Parker Solar Probe. This was not merely a rocket, it was a testament to the combined expertise of thousands of minds and billions of dollars in investment. It was designed to do the impossible, to touch the sun, flying closer to that raging nuclear furnace than any object in history. To survive this, the probe is armoured with a cutting-edge heat shield, allowing it to endure temperatures exceeding 2,500 degrees Fahrenheit. But its most significant achievement isn't its endurance, it is its speed. The Parker Solar Probe does not achieve its velocity through the chemical wall of raw engine power alone. Instead, it performs a complex, decades-long gravitational ballet, using the planet Venus as a celestial tether. With each flyby, the probe steals a microscopic fraction of the planet's orbital energy, converting altitude into a terrifying, screaming velocity. It is humanity's single greatest effort to navigate the cosmic void. Right now, in this very moment, the Parker Solar Probe is hurtling through space at 430,000 miles per hour. To the human mind, this number is a meaningless abstraction, so let us collapse it into a scale you can feel. At this velocity, you could circle the entire Earth in under 4 minutes. If you were standing in New York, you could blink twice, and by the time your eyes opened, the spacecraft would have already passed Los Angeles, crossed the Pacific, and be approaching the islands of Hawaii. It moves fast enough to cross the entire continental United States in under 25 seconds. This is speed that would vaporize you instantly upon contact with any solid matter. It is the absolute pinnacle of what we can achieve. And yet, when we place this record-breaking achievement against the backdrop of the amnesia clock, the vertigo returns. We must confront the crushing truth. Even at 430,000 miles per hour, the distance a human could actually cross in a single lifetime is not limited by our money or our willpower, but by a barrier woven into the very fabric of reality. At this peak, human velocity, reaching our nearest stellar neighbour, Proxima Centauri, a star a mere 4.24 light-years away, would still require approximately 6,600 years. To put this in human terms, if a traveller had boarded a ship moving at Parker's maximum speed, at the exact moment the ancient Sumerians were inventing writing and the first city-states were rising in Mesopotamia, that ship would only now be approaching its destination. Entire civilizations have risen, flourished and vanished into the dust, while that craft drifted, silent and lonely, through the interstellar dark. The mathematics become even more disturbing when we look at the span of a single human life. If you spent 80 years, your entire biological existence, travelling at the fastest speed humanity has ever recorded, you would cover roughly 3 trillion miles. It is a number with 12 zeros, a distance that sounds unimaginably vast until you measure it against the cosmic map. That lifetime of travel equals exactly 0.05 light-years. You would spend your entire existence in the dark, and you would die having covered barely 1% of the distance to the closest star. You would never come close to leaving your own stellar neighbourhood. It is like walking non-stop for your entire life and discovering you have crossed less than a single city block, because the map was never drawn to our scale in the first place. But perhaps the solar system is our home, and we simply need to reach its edge. Even this intuition is a lie. We often think of our home ending at the orbit of Pluto, but the Sun's gravitational grip, the true boundary of our solar system, extends to the Oort cloud, a frozen shell of ancient cometary debris. At our current maximum speed, reaching just the inner edge of this cloud would require 600 years of continuous travel. An entire human lifetime spent at the very peak of our engineering wouldn't even allow you to escape the Sun's gravitational family. Measured against the scale of our local cosmic neighbourhood, your entire life of travel would accomplish less than crossing from Manhattan to Brooklyn. You would be a space traveller who never actually made it past the front porch. Consider Voyager 1, the farthest human-made object in the void. For nearly half a century, it has been hurtling away from us, covering 15 billion miles, a distance so vast it took nearly 50 years to achieve. Yet, if the journey to our nearest neighbour was a cross-country road trip from New York to Los Angeles, Voyager 1 would have travelled roughly 100 feet in 47 years. You could still see the ship from your driveway. Your neighbours would watch you age from youth to retirement, and your car would remain visible from their kitchen window, a stationary ghost on a map that refuses to move. Voyager 1 has been travelling for nearly 5 decades, yet it has covered a distance that light, the universe's true benchmark, crosses in approximately 20 hours. This is the unsettling implication of the Parker limit. Our greatest engineering achievement is essentially a snail's crawl on the cosmic map. We are not explorers. We are inhabitants of a microscopic oasis embedded in an interstellar desert so large that our boldest machines barely flicker before they are extinguished. We often imagine progress as a straight line, that if we simply build a bigger rocket or a better engine, the stars will eventually fall within our reach. But space does not reward the incremental. The gulf between planets and stars is not just large, it is exponential. To make the light years negotiable, we do not need better navigation. We need a fundamentally different relationship with time itself. If you were to board the Parker Solar Probe today, you would die long before you reached the halfway point to the nearest star. Your children would die in the dark. Your grandchildren would die in the dark. The amnesia clock would tick on, recording the fall of the very civilization that launched you, while you remained stuck in the sun's backyard. We are living in an era where speed has failed us. We have mastered the art of the gravitational assist. We have built shields that can withstand the touch of a star, and yet we remain cosmically isolated, trapped in a local pocket of matter that we may never truly leave behind. The unsettling truth is that for a biological being, the stars are not just far away. They are categorically unreachable by the means we currently possess. We are like a species of flightless birds on a tiny island in a vast ocean, staring at distant shores we can see with our telescopes, but can never touch with our hands. The stars remain fixed not because they are inherently unreachable, but because distance overwhelms duration. To reach further, we must stop looking at our engines and start looking at the loophole Einstein discovered. Because while distance may be a fixed wall, time is not. Behind us, the amnesia clock begins to hum. It is a warning that our time is running out. Every second we wait to find a new way to move, another galaxy slips forever beyond our reach, carried away by the expansion of space-time itself. The window is closing, and to jump through it, we must learn to walk not through space, but through the fabric of time itself. On the forward bulkhead of our vessel, the amnesia clock has finally begun to move. For what felt like an eternity during our crawl through the chemical age, its obsidian hand remained paralysed, a mocking reminder that we were essentially stationary in the eyes of the cosmos. But now, as the blue-white glare of the stars ahead begins to collapse into a singular, blinding needle of light, the clock has found its rhythm. It no longer waits for centuries of human struggle to pass before it nudges forward. It is beginning to record the literal unravelling of the world we left behind. Imagine you are the traveller aboard this hypothetical craft. Inside the hull, the environment is serene. The hum of the life support system is a steady, comforting maternal heartbeat. The lights are set to a soft amber to mimic a terrestrial sunset. To you, everything feels normal. Your coffee still takes 3 minutes to brew. Your heart still beats 60 times a minute. Your cells still divide at the same measured pace. You feel no different than you did on the morning you said your final goodbyes on a launch pad in Kazakhstan or Cape Canaveral. On this particular evening, you are holding a small, solitary celebration. You have reached a velocity that was once considered the fever dream of science fiction, 99.9% of the speed of light. You pour a glass of wine and look at the calendar on your digital display. It has been exactly 365 days since the engines reached peak thrust. You blow out a single candle on a cake to mark your first anniversary in the deep void. You feel a sense of triumph. You have survived a year in the most hostile environment known to man, and you are currently hurtling toward the stars faster than any human in history. But as you blow out that candle, you are unaware of the mathematical violence being visited upon the timeline of your species. To understand the celebration in this cabin, we must return to Albert Einstein, the patent clerk from Bern. He was the first to realise that the speed of light is not just a high velocity, but a universal constant that space and time are forced to negotiate with. If light must always travel at 186,000 miles per second, then something else has to give. That something is time itself. This is the loophole in the fabric. The faster you move through space, the more slowly you are permitted to move through time. In physics, we measure this stretching of time using a value called the Lorentz factor, or gamma. At the everyday speeds of a car or even the Parker Solar Probe, gamma is effectively 1. Time for the driver and time for the pedestrian are the same. But as you approach the speed of light, the curve of gamma doesn't just rise, it explodes. At the 99.9% mark where your ship is currently cruising, gamma reaches a value of 22. This number, 22, is the governing law of your new existence. It represents the ratio of your life to the life of the Earth. It means that for every second that ticks by on your wristwatch, 22 seconds vanish back home. For every hour you spend sleeping in your bunk, nearly an entire day is deleted from the Earth's calendar. And for that one ship year you just celebrated with your single candle, 22 years of human history have been incinerated behind you, while you were busy monitoring your fuel levels and celebrating your anniversary. The world you left behind moved at a frantic, terrifying pace. On Earth, a child who was born on the day you launched is now a young adult, perhaps graduating from university or starting their first job. The parents you hugged goodbye have aged 2 decades. Their hair has turned silver. Their faces have mapped out the passage of a generation you did not witness. The political leaders who funded your mission are likely retired or dead. The very technology you are using is now 22 years obsolete in the eyes of the engineers back home. This is the profound vertigo of time dilation. It is not a psychological trick or a byproduct of high-speed travel. It is a fundamental restructuring of your relationship with reality. You have found a way to cheat the vast distances of the universe by slowing your own aging, But the universe is a cruel accountant. It demands that you pay for your distance in the currency of human connection. The unsettling implication of this journey is that you haven't just travelled through space. You have unlocked the door to the future, and there is no way to ever go back. If you were to turn the ship around right now and spend another ship year returning at the same speed, you would arrive home having aged only 2 years. But the Earth you return to would be 44 years older than the one you left. You would be a young person stepping into a world of elderly peers. You would find that your now is forever out of sync with the now of your species. You are a temporal exile, a ghost, haunting a future that has moved on without you. This creates a psychological isolation that no training can prepare you for. Consider the Alice and Bob paradox, the classic story of the twins. Alice boards the relativistic ship, while Bob stays on the ground. When Alice returns, she is still in her youth, but she finds Bob has gone grey, his life nearly spent. In your case, at 99.9% of light speed, this gap is even more brutal. A round trip to a star 25 light years away, like Vega, would take you only about 2 years of ship time. But when you touch down on the tarmac of Earth, 50 years would have passed. You would be 27 years old, looking for a home and a family that has likely forgotten the sound of your voice. This loophole changes the answer to our central question: how far can we go? In a single biological lifetime of 80 years, if you could maintain this 99.9% velocity, you wouldn't be limited to the front porch of the Oort cloud. You wouldn't be trapped within the 0.05 light-year radius of the Parker probe. Instead, your 80 years would stretch across 1,760 years of Earth time. You could cross over 1,100 light-years of distance. You could visit the Orion Nebula, witnessing the birth of new stars and the collapse of ancient gas clouds. You could see things that no telescope on Earth will ever resolve. But you would be doing so as a man or woman without a country and without a time. Every light year you conquer is another century of human history you are willing to forfeit. To reach the stars, you must be willing to watch the amnesia clock tick through the rise and fall of everything you once loved. You must accept that by the time you reach your destination, the language you speak might be a dead tongue, and the civilization that built your ship might be nothing more than a series of ruins studied by archaeologists who have no memory of your name. This is the true price of the stars. Relativity has given us a key to the cosmos, but it is a key that only turns in one direction. We have learned how to walk through the fabric of time, but in doing so, we have discovered that the universe is a place of absolute, crushing loneliness for those who move too fast. As you sit in your cabin, the light of your anniversary candle flickering in the artificial air, you realise that the stars ahead are no longer just points of light. They are islands of the future, and as you move toward them, the Earth behind you is fading, not just into the distance, but into the deep, unreachable past. The amnesia clock on our forward bulkhead is no longer the only sound in the ship. There is a new microscopic music, a faint metallic hissing against the outer hull that sounds like sand hitting a window in a desert storm. For decades, we believed the void was empty, a pristine stage where only gravity and light played their parts. But as our velocity climbs, the nothingness of space is beginning to scream. The hand of the clock continues to nudge forward, recording the death of civilizations we left behind, but our attention has shifted. We are no longer watching the time, we are watching the hull. We were raised on the lie that interstellar space is a perfect vacuum, a silent cathedral of absolute stillness. But in 2016, a researcher named Thiem Huang and his collaborators sat before a screen of numbers that described a subtle, microscopic murder. Huang wasn't looking at massive asteroids or rogue planets. He was focused on the interstellar medium, ISM, the diffuse gas and dust that fills the gaps between the stars. In our local neighbourhood, a region of space known as the local bubble, the ISM is incredibly sparse, containing on average just one hydrogen atom for every 10 centimetre cube. To our terrestrial instincts, this is as close to nothing as the universe allows, but Huang's calculations revealed a terrifying transformation that occurs when nothing meets a significant fraction of light speed. On an unremarkable afternoon, he quantified what happens when a spacecraft reaches 20% of the speed of light. At this velocity, the void is no longer empty. It becomes a sleet of high-energy kinetic violence. Imagine you are standing at the forward observation port of our ship. You're looking out at a sugar cube volume of space ahead of you. It contains exactly one atom of hydrogen. At the speeds we are currently travelling, that single lonely atom is not a gas. It is a lethal bullet. When our ship's hull strikes that atom at 20% light speed, the laws of kinetic energy, where energy equals half the mass times the velocity squared, dictate a brutal outcome. The velocity is so high that the energy of the impact is no longer measured in the language of chemistry, but in the language of nuclear physics. Huang found that every single hydrogen atom hitting the forward hull at these relativistic speeds behaves like a tiny high-energy proton. It doesn't just bounce off, it vaporizes a microscopic crater into the metal. The light elements like hydrogen and helium deposit heat, but the heavier tracers, the wandering atoms of oxygen and iron forged in the hearts of long-dead stars, act as extra massive projectiles that leave permanent jagged scars in our armour. The math is devastatingly clear. As we journey toward Proxima Centauri, our forward hull is being systematically eaten by the nothingness of the void. Huang's work showed that even over a short 4 light-year journey, the forward surface of a craft would be vaporized to a depth of 0.5 millimetre. This sounds manageable until you realise that space is not just filled with atoms, it is filled with dust grains, silicate and carbonaceous molecules that have clumped together into tiny microscopic pebbles. A single grain of dust, just a micrometre across, carries a trillionth of a gram of mass, less than a speck of ash. But at 10% of light speed, that speck hits our hull with the kinetic energy of a handgun bullet. At 50% of light speed, the energy of that same microscopic grain explodes to 250,000 joules, the equivalent of being struck by a high-powered rifle round. And at 90% of light speed, the velocity required to make the amnesia clock truly move, a single microscopic dust grain delivers the energy of several kilograms of TNT. The void is not a sanctuary. It is a firing range where we are the only target. 4. The unsettling truth of our journey is that we are being subjected to a form of interstellar murder. Even if the hull holds, the radiation will not. As those hydrogen atoms are stripped of their electrons upon impact, they become a continuous sleet of high-energy protons that can penetrate deep into the ship's interior. Oleg Semyonov, another architect of our cosmic imprisonment, calculated in 2006 that the crew of an inadequately shielded ship would be subjected to radiation levels comparable to the core of a nuclear reactor. Without massive protection, the starship arrives at its destination perfectly intact, but it is a ghost ship, carrying a crew of radiation-blasted corpses. To survive this, we have been forced to accept a shielding debt. To protect your biological cells from the proton sleet, the ship requires a barrier of profound thickness. A titanium windshield, centimetres thick, might suffice at 20% light speed, but as we push toward the loophole of time dilation, the requirements become gargantuan. We need a metre-thick shield of water or lead wrapping around the entire vessel to stop the secondary radiation and the relentless bombardment of cosmic rays. Water is the most elegant solution because, as biological beings, we must carry it anyway. We wrap our living quarters in thousands of tons of it, a literal heart of water to protect us from the cold fire of the stars. But here is where the amnesia clock begins to mock us again. The unsettling implication of the shielding debt is that the universe has designed a perfect system of check and balances to keep life grounded. To survive the relativistic journey, you must add mass. To stop the bullets of the void, you must carry a shield that weighs thousands of times more than the crew it protects. But every kilogram of water and lead we add to our hull is a kilogram that must be accelerated by our engines. The tyranny of the rocket equation returns with a vengeance. The more armour we add to survive the murder of the ISM, the more fuel we require. The more fuel we carry, the more mass we have. Eventually, the math reaches a point of practical impossibility. You find yourself trapped in a paradox. To go fast enough to reach the stars in a lifetime, you must have a ship so light it can accelerate. But to survive going that fast, you must have a ship so heavy it can no longer move. We are permanently quarantined not just by the distance, but by the very matter of the universe. Space is not nothing. It is a dense physical barrier that demands a price in mass that our engineering can no longer pay. We are like knights in armour so thick and so heavy that we can no longer lift our swords to strike or our feet to walk. As the hissing against the hull continues, you realise that the amnesia clock isn't just measuring the time we've lost, it is measuring the thickness of the metal between us and the void. We are paying our debt in millimetres of ablation, watching our shield vaporise into the dark. We are attempting to survive a microscopic war of attrition, hoping that we reach the light of the next sun before the nothingness finally reaches us. As we drift deeper into the interstellar desert, the amnesia clock on our forward bulkhead continues its cold, rhythmic judgment of our journey. We have looked into the loophole of time dilation, and we have felt the lethal friction of the void. But now we must confront the most desperate wager in the history of our species. To move a vessel heavy enough to survive the interstellar murder of the vacuum, we need a fire that does not merely burn, but one that consumes the very essence of matter itself. We are entering the era of the antimatter gamble, where the price of speed is no longer measured in fuel tanks, but in the total energy output of our entire civilization. The story of our ultimate fuel does not begin in a shipyard or a launch pad, but in the sterile, high-tech silence of a laboratory buried deep beneath the border of France and Switzerland. In 2023, inside the sprawling complex of CERN, a team of scientists achieved a feat that, to our ancestors, would have seemed like capturing a ghost. Using a complex web of magnetic fields and a near-perfect vacuum, they successfully stored a collection of antiprotons for exactly 16 hours. To a layman, 16 hours is a blink of an eye, a mere afternoon. But in the language of the cosmos, it was a revolution. It was the first time we had successfully held the most volatile substance in the known universe long enough to truly contemplate its power. Antimatter is not just better fuel. It is the theoretical end of the road for propulsion. In every other engine we have ever built, from the wood fires of the ancients to the nuclear reactors of our modern age, we have only ever nibbled at the edges of energy. When we burn hydrogen, we are only extracting a microscopic fraction of the energy locked within its molecular bonds. Even in the heart of a nuclear fusion reactor, the process that powers the sun, we are only converting about 0.7% of the fuel's mass into energy. But antimatter is different. When a particle of matter meets its antimatter counterpart, they don't just react, they annihilate. They vanish from existence in a flash of pure radiation, converting 100% of their combined mass into raw, blinding energy. The energy density of this reaction is almost impossible to comprehend. A single gram of antimatter annihilating with a gram of normal matter releases approximately 180 trillion joules. This is the explosive yield of the Hiroshima atomic bomb, concentrated into a space smaller than a marble. It is enough energy to power an average household for 4.5 years, or to accelerate a small spacecraft to velocities that make the Parker Solar Probe look like a stationary object. If we could harness this fire, the map of the stars would finally begin to shrink. An antimatter engine would work by directing the products of this annihilation, sprays of high-energy particles called pions and muons, through a magnetic nozzle to generate thrust. Because these particles exit the engine at a significant fraction of the speed of light itself, the chemical wall of Tsiolkovsky is finally shattered. Iska, with just 100 kilograms of antimatter, we could theoretically push a probe to 30% of light speed, reaching a star like Epsilon Eridani in just 35 years. If we could scale up to a few thousand kilograms, we could reach the 90% threshold where the amnesia clock truly begins to work in our favour, compressing decades of interstellar travel into just a few years of shipboard time. But this is where the antimatter gamble reveals its terrifying cost. The universe does not give up its ultimate secret for free. The first part of the gamble is production. Antimatter does not exist naturally in our universe in any meaningful quantity. It is a mirror image of reality that was almost entirely destroyed in the first moments of the Big Bang. Every single antiproton we wish to use for our journey must be manufactured, one by one, inside massive particle accelerators. The process is catastrophically inefficient. To create antimatter, we must smash particles together at nearly the speed of light, consuming roughly 10 billion times more energy than the resulting antimatter ultimately stores. This leads to an unsettling implication that forces us to realize just how isolated we truly are. To produce enough antimatter to fuel a single human mission to the nearest star, just a few kilograms of fuel, we would need to run every power plant on Earth for centuries. We would have to dedicate the entire electrical output of our global civilization, every wind turbine, every nuclear core, and every solar panel for hundreds of years, just to fill the tank of one ship. At our current global production rate of roughly 10 to 20 nanograms per year, accumulating enough fuel for an interstellar probe would take approximately 5 billion years, roughly the remaining lifespan of our Sun. The gamble, then, is not just about the technology of the engine, but about the longevity of our civilization. We would have to become a species that can plan and labour across millennia, building antimatter factories on a scale that dwarfs anything in human history, all for a journey that the people who paid the energy debt will never live to see. Even if we solve the production crisis, we face the second part of the gamble: storage. Because antimatter annihilates instantly upon contact with any normal matter, you cannot simply put it in a tank. It must be suspended in a perfect vacuum using powerful, uninterrupted magnetic fields. The fuel for your ship is, quite literally, a flying bomb of unimaginable power. If the magnetic containment fails for even a fraction of a second, due to a hardware glitch, a stray dust grain impact, or a loss of power, the resulting explosion would be brighter than a star, vaporizing the ship and everyone on board in a microsecond. To travel with antimatter is to live on top of a caged sun, knowing that your survival depends on a magnet that can never, ever be turned off. As we look at the amnesia clock, we realize the gravity of our situation. We have found the key to the stars, but it is made of a material so expensive and so dangerous that we may never be wealthy or brave enough to use it. We are a Type 0 civilization trying to buy a ticket for a Type 2 journey. We have discovered the most energy-dense fuel possible, only to realise that we are permanently quarantined by our own poverty. The stars remain out of reach not because we lack the physics, but because we lack the scale. We are like a child who has discovered that a single drop of fuel could take them across the ocean, but finds that the drop costs more than the entire value of their home. We sit in the dark of our solar system, staring at the 16-hour storage record at CERN, realizing that the bridge to the future is a structure we haven't yet learned how to build. But while we gamble with the fire of the atom, the universe itself is changing. Even as we struggle to find a way to move faster, the space between us and our destinations is stretching. The window for our departure is not just far away, it is actively closing. For every century we spend trying to solve the antimatter production crisis, the galaxies at the edge of our vision are slipping forever beyond our reach. The amnesia clock on our forward bulkhead has begun to pulse with a new, frantic energy. It is no longer merely a record of the civilizations we have outlived or the fuel we have burned. It has become a countdown. We have spent our journey obsessing over the chemical wall and the Parker limit, believing that the stars were stationary targets waiting for us to eventually find the keys to their gates. We treated the universe as a static map, a vast but unchanging territory that would remain patient while we mastered the fire of antimatter. But as we stare at the clock's obsidian hand, we are forced to confront a reality that no engine can overcome. The map itself is stretching, and the destinations we once thought were ours are being pulled into the unreachable deep. To understand why the very geometry of the cosmos is conspiring against us, we must look to a quiet corner of the University of Oxford. In the early 21st century, a researcher named Toby Ord, working at the Future of Humanity Institute, sat down to calculate the ultimate limits of human ambition. He wasn't looking at the next decade or the next century, but at the entire future trajectory of our species. Ord sought to define what he called the affectable universe, the maximum extent of space that humanity, or whatever we evolve into, could ever hope to influence if we began our journey today at the speed of light. Ord's findings provide the first true sense of cosmic vertigo. We have been told that there are upwards of 2 trillion galaxies in the observable universe, a number so vast it suggests an infinite playground for exploration. But Ord revealed that the observable universe is a grand illusion. Because space is expanding, the galaxies we see in our telescopes are not where they appear to be. Their light has travelled for billions of years to reach us, painting a picture of a universe that has already moved on. Ord identified a sphere with a radius of 16.5 billion light-years as our true, affectable universe. Within this sphere, there are approximately 20 billion galaxies. To our terrestrial minds, 20 billion galaxies sounds like a limitless frontier, but it represents a mere 1% of the total galaxies we can see. The other 99% are already beyond our reach, not because we lack the speed, but because the space between us is growing faster than any light speed signal could ever hope to cross. The engine behind this cosmic theft is a mysterious pressure known as dark energy. For most of human history, we believed gravity would eventually slow the expansion of the universe, perhaps even pulling it back into a big crunch. But in 1998, astronomers discovered the opposite. The expansion is not slowing, it is accelerating. Dark energy acts like a persistent, invisible tension that makes up roughly 70% of the universe's total energy content, stretching the fabric of space-time itself. Imagine the universe as a loaf of rising raisin bread. We are a single raisin, and every other galaxy is another raisin embedded in the dough. As the bread rises, the raisins don't move through the dough. Rather, the dough between them expands. The further away a raisin is, the more dough there is to expand, and the faster it recedes from us. At a certain distance, the Hubble horizon, the space between us is expanding at the speed of light. Any galaxy beyond that horizon is effectively falling off the edge of our world. Even if we were to launch a ship at 99.99% of light speed right now, we would never catch them. We are like swimmers in an ocean where the water itself is being created in front of us faster than we can kick. This is where the amnesia clock takes on its most ominous rhythm. Toby Ord calculated the cost of our procrastination, and the number is a haunting indictment of our hesitation. Every single year that humanity remains huddled in our own solar system, debating the budgets of rockets and the safety of nuclear cores, an average of 3 entire galaxies slip permanently and irrevocably beyond our reach. But think of the scale of that loss. Each of those galaxies contains hundreds of billions of stars. Each of those stars likely hosts planets, moons, and perhaps the stirrings of other lives. Every second we wait to launch an entire cosmic neighbourhood, a volume of space that could have supported 1 billion generations of human descendants, is being incinerated by the expansion of space. By the time you finish reading this sentence, several thousand star systems have crossed the event horizon. They are still visible to our telescopes, but they are ghosts. Their light will reach us for a time, but their physical reality is now in a separate universe from ours. The unsettling implication of this discovery is that we are living in a closing window of opportunity. If we wait too long, we will enter what Toby Ord calls the era of isolation. In a few billion years, the cosmological event horizon will have shrunk so much that even the Andromeda galaxy might become unreachable if we haven't already merged with it. Future astronomers, born trillions of years from now, will look up at a night sky that is utterly, terrifyingly empty. They will see no other galaxies, no cosmic microwave background, and no evidence of the Big Bang. They will conclude that their single, lonely galaxy is the entire universe, never knowing that there were once 2 trillion sisters dancing in the dark. Every tick of our ship's clock is now a reminder of a galaxy we have lost. We have traded the infinite for the finite. We often talk about the quarantine of the speed of light, but the real prison is dark energy. It has drawn a line in the sand 16.5 billion light years away and told us, this far and no further. No amount of clever engineering or antimatter fuel can break that boundary. We are in a race against the very fabric of reality, and we are losing 3 galaxies every year. This realization shifts the weight of our mission. Interstellar travel is no longer just a luxury for a curious species. It is an urgent, desperate escape from the era of isolation. If we stay, we are choosing to become a living fossil in a universe that will eventually forget we ever existed. We are out here, watching the amnesia clock, because we understood that the stars are not just far away, they are actively running away from us. But as we push our engines toward the limits of the affectable universe, we realize that even if we can beat the expansion, we cannot beat the social gravity of the journey. To reach those distant galaxies, we must become something other than human. We must become a species that can survive for centuries in a closed metal box, birth children who will never see a sun, and maintain a culture that has no connection to the world that birthed it. We are moving from the physics of the void into the psychology of the generationship, a social experiment where the traveller and the prisoner are one and the same. The amnesia clock on our forward bulkhead has slowed its frantic pace. In the chapters of our journey where we chase the edge of light, the clock's obsidian hand swept through centuries of human history with a terrifying, blurred velocity. But now, we have made a different kind of peace with the void. We have accepted that the chemical wall may be too high and the antimatter gamble too expensive to ever truly master. To reach the stars, we have abandoned the pursuit of speed and embraced the endurance of the species. We are no longer trying to outrun time. We are trying to inhabit it. We have entered the era of the generation ship, a metal womb drifting through the dark at a mere 1% of light speed, where the journey is no longer a mission, but a permanent state of existence. To understand why this transition is so fraught with peril, we must look back to a specific, humid afternoon in September 1991, in the high desert of Oracle, Arizona. There, a group of 8 researchers dressed in futuristic jumpsuits waved goodbye to the world and stepped through a heavy airlock into a 3-acre glass and steel cathedral known as Biosphere 2. It was intended to be the ultimate rehearsal for life among the stars, a perfectly closed ecological loop containing a miniature rainforest, a desert, a marsh, and a tiny ocean. For 2 years, these 8 biospherians were to live entirely off the recycling of their own waste, the oxygen of their own plants, and the food grown in their own soil. But the dream of a perfect loop quickly began to unravel into a waking nightmare. Within months, the atmosphere inside the glass began to turn toxic. The soil, enriched with too much organic matter, began to host a population of oxygen-consuming microbes that breathed faster than the plants could photosynthesize. Oxygen levels plummeted from a healthy 21% to a suffocating 14%, the equivalent of living at an altitude of 13,000 feet. The biospherians became lethargic, their minds clouded by the rise of carbon dioxide. Hunger became a constant gnawing companion as crop yields failed, and the crew began to lose significant body weight. Perhaps most tellingly, the social fabric of the group fractured. The 8 researchers split into 2 bitter factions, refusing to speak to one another, their shared sense of purpose replaced by the primal friction of confinement. Biosphere 2 was a 2-year experiment on a planet that could still provide rescue. On a generation ship, there is no outside world to pump in emergency oxygen. This is the scientific idea that underpins our new reality. If we cannot go fast, we must go slow. If we cannot reach a star in a single lifetime, we must build a ship large enough to support a population that can live, reproduce, and die across centuries. Such a craft would be less like a vehicle and more like a drifting city, perhaps a Stanford torus, a rotating ring over a mile in diameter that uses centrifugal force to simulate the comforting pull of Earth's gravity. Inside, thousands of people would tend to vertical farms, manage complex water recycling systems, and maintain a mechanical sun. So the math of population genetics suggests that to avoid the catastrophe of inbreeding and maintain a healthy gene pool over 500 years, such a ship would require a minimum of 500 to 1,000 individuals, an isolated tribe cast into the ultimate desert. The unsettling implication of this social experiment is a form of genetic and cultural exile that no other human experience can match. On a generation ship, the people who eventually arrive at the destination are not the explorers who chose to leave. They are the great-great-grandchildren of the original crew, individuals who were born into a metal cylinder they never asked to inhabit. They are strangers to Earth in the most literal sense. To them, the concept of an open sky or natural rain is not a memory, but a mythological legend passed down through grainy digital files and ancient storybooks. They have spent their entire existence in an environment where every breath of air is a mechanical gift, and every sip of water has passed through the bodies of their ancestors 1,000 times over. This creates a profound psychological vertigo for the inhabitants of the void. As the decades turn into centuries, the mission's original purpose can begin to erode. Why continue toward a star you will never see? Why maintain the complex engineering of a ship built by a civilization that has likely vanished into the dust of the amnesia clock back home? There is a terrifying risk that technical knowledge will be lost over the generations, turning the ship's vital systems into holy relics that the crew operates by rote ritual rather than understanding. If a critical system fails and the engineers of that generation have forgotten how to fix it, the ship becomes a drifting tomb, its inhabitants unable to escape the metal cage of their own heritage. The people who step onto the soil of a new world after such a journey will be biological anomalies. They will have evolved in a world of artificial light and recycled air, their immune systems unaccustomed to the raw, unfiltered biology of a planet. They will look back at the sun, now just a dim, unremarkable spark in the rear observation port, and feel no connection to the blue marble of history. To them, Earth is not home. It is a ghost story told in the hallways of a machine. They have become a new branch of the human lineage, one defined not by the land that birthed them, but by the void that shaped them. As we look at the amnesia clock, we realize that the generation ship is the ultimate sacrifice of the individual for the sake of the species. We have accepted that a human life is too short to cross the interstellar sea, and so we have turned our descendants into the fuel for our journey. We are out here, drifting at 1% of light speed, watching the hand of the clock erase our origins, knowing that the people who finally reach the light of another sun will be a species we might no longer recognize as ourselves. But even as we contemplate the slow, heavy march of the generations, we must face the reality that some among us will never accept the cage of the metal cylinder. There are those who still crave the loophole Einstein discovered, those who would rather be temporal exiles than prisoners of a hallway. We are moving from the collective struggle of the generation ship into the singular, crushing isolation of the high-speed traveller, the person who reaches the stars in a single life, only to find that they have lost everything else in the process. On the forward bulkhead of our vessel, the obsidian hand of the amnesia clock has begun to sweep with a terrifying, blurred velocity. Throughout our journey, we have treated the clock as a ledger of fallen empires and vanished cities. But as we push our engines into the deepest reaches of the relativistic realm, the clock is no longer recording history, it is incinerating it. We have moved beyond the chemical age and the antimatter gamble, and we are now inhabiting a reality where the ticking of our own hearts is the only thing that remains in sync with our origin. To look at the clock now is to witness the absolute erasure of everything we once were, to understand the profound loneliness that defines this stage of our journey. We must look back to a pair of siblings whose story has become the definitive tragedy of the space age. They are known in the annals of physics as Alice and Bob, the famous twins who served as the human faces of Einstein's most disturbing prediction. In our hypothetical narrative, Alice is the explorer, the one who boards the relativistic starship, while Bob is the anchor, the one who remains on the surface of the Earth to watch the sky. On the morning of Alice's departure, the twins are 25 years old, identical in every biological metric. They share the same memories of childhood, the same genetic predispositions, and the same rhythm of aging. But as Alice's ship clears the Oort cloud and begins its relentless acceleration toward the speed of light, their shared now begins to fracture. Alice feels nothing unusual. Her coffee still brews in 3 minutes, and her cells divide at their normal, measured pace. To her, the journey is a series of quiet shipboard routines. But back on Earth, Bob is witnessing a mathematical violence being visited upon his sister's timeline. This is the birth of the twin paradox, a measured and verified phenomenon where motion through space steals from motion through time. In 1971, physicists Joseph Haffel and Richard Keating proved this wasn't just a thought experiment when they flew atomic clocks around the world on commercial airliners and found they returned ticking behind those left on the ground. But for Alice and Bob, the disparity is not measured in nanoseconds, it is measured in lifetimes. Imagine Alice decides to undertake a truly ambitious journey, a round trip to the galactic centre, the violent, brilliant heart of the Milky Way, located some 26,000 light-years from Earth. To accomplish this within her own biological lifespan, Alice's ship must maintain a velocity of 99.99% of the speed of light. For Alice, the outbound leg of the journey is an incredible expedition that lasts approximately 30 subjective years. She witnesses the constellations ahead shift towards the ultraviolet, their light blue shifting into a blinding needle of radiation. She sees the universe bunching into a narrowing cone of light ahead of her, a phenomenon known as relativistic aberration. She spends 3 decades exploring the supermassive black hole at the centre of our galaxy, Sagittarius A star, witnessing phenomena that no telescope on Earth could ever resolve. When she finally turns the ship around and returns to Earth, she has aged exactly 60 years. She is now an 85-year-old woman, her body bearing the natural marks of a life well lived. She prepares to step off the ship, expecting perhaps to be met by the elderly descendants of her brother, or at least a world that remembers her name. But as she opens the airlock, she is struck by a sense of absolute cosmic vertigo. Because Alice travelled at 99.99% of light speed, her subjective 60 years of travel have spanned 520,000 years of Earth history. The amnesia clock has not just moved, it has completed thousands of revolutions. Her brother Bob did not just die centuries ago. He has been dead for 500,000 years. His very bones have returned to the dust, and the dust itself has been recycled through the crust of the earth a dozen times over. The civilization that launched Alice is not just gone. It is archaeological prehistory, its languages forgotten, its monuments ground into unrecognisable silt by the slow march of tectonic plates. This is the scientific idea that serves as the final, unbreakable lock on our cosmic prison. Time dilation turns interstellar travel into a form of permanent exile. You have found a loophole that allows a human lifetime to stretch across the stars, but the universe demands that you pay for that distance with the total forfeiture of your connection to the world you left behind. The unsettling implication of Alice's return is that she is no longer just a traveller. She is a living fossil. Modern humans, Homo sapiens, have only existed for roughly 300,000 years. By returning 520,000 years in the future, Alice has outlived her own species. The beings who now inhabit the Earth, if any inhabit it at all, would be as different from Alice as she is from the primitive hominids who first walked the African savannah. She has returned to a world where she is a biological anomaly, an ancient artifact from a vanished epoch, unable to even interbreed with the descendants of the people she once loved. This is the crushing solitude of the relativistic traveller. You can see the universe, you can touch the heart of the galaxy, and you can witness the birth of stars, but you can never share it with the world that birthed you. Every light year you conquer is another century of human history you are willing to incinerate. Interstellar exploration, when pushed to these extremes, severs the fabric of human relationship absolutely. You become a messenger who can never bring the message home. Consider the psychological weight of this isolation. As Alice travelled, she could have received broadcasts from Earth, but they would have arrived in a frantic, compressed fast forward. She would have watched centuries of history unfold in the time it took her to eat a meal. She would have seen the rise and fall of world religions during her morning exercise, and the extinction of entire languages before her evening sleep. To the relativistic traveller, the earth is not a stable home. It is a flickering candle, burning down to nothing while they remain suspended in the amber of their own speed. The vertigo of this experience reshapes our understanding of home. We were raised to believe that home is a set of physical coordinates, a house, a city, a planet. But relativity teaches us that home is actually a temporal context. It is a shared now with the people we know. When Alice boarded her ship, she didn't just leave a place, she left a time. And in the universe of Einstein, time is a one-way street. You can move forward into the future as fast as your engines will carry you, but you can never ever go back to the now you abandoned. As Alice stands on the surface of an unrecognizable future Earth, she realizes that the stars she explored were not just destinations in space, but islands of the future. And as she moved toward them, the world behind her was fading, not just into the distance, but into the deep, unreachable past. She is the last human of her era, a ghost haunting a world that shares only her physical coordinates, but none of her history. We are out here watching the amnesia clock, because we understood that the price of the stars is the surrender of our own era. We have chosen to become temporal exiles, trading the comfort of the shared human narrative for the cold, lonely majesty of the infinite. But even as we accept this isolation, we realize that there is one final horizon, one last boundary that not even Alice's perfect engines can overcome. For the universe itself is not a static stage, and the very ground we are walking on is expanding, threatening to carry the stars away faster than we can ever hope to run. The amnesia clock on our forward bulkhead has reached the end of its mechanical patience. For the duration of our journey, we have watched its obsidian hand sweep away the history of our species, recording the rise and fall of empires as though they were mere heartbeats in the dark. We have transitioned through the eras of fire and atoms, moved through the loophole of time dilation, and paid the shielding debt in millimeters of vaporized hull. Now, as the vessel begins its final approach to the sovereign territory of an entirely different galaxy, the clock is no longer a tool of measurement. It has become a monument to a world that no longer exists in any form other than our memory. Imagine you are the traveller standing at the edge of the Andromeda galaxy. You have achieved the impossible. You have crossed the 2.5 million light-year void between island universes within your own biological lifespan. To you, the journey has been an intense claustrophobic expedition of perhaps only a few subjective years. Provided your engines maintained a velocity where the Lorentz factor reached into the millions, your heart has beaten a standard number of times, and your hair has only just begun to show the silver of middle age. You step toward the rear observation port and look back toward the local group, searching for the spark that once defined your existence. You point your most powerful instruments toward the coordinates of the Milky Way, searching for a specific, unremarkable yellow star on the edge of a spiral arm. But the sun, you remember, the brilliant, life-giving furnace of your childhood, is gone, because you travelled at extreme relativistic speeds. 2.5 million years of Earth history have been incinerated behind you. In that vast gulf of time, the sun has moved through its own inexorable life cycle. You find only a dim, cooling ember, a dead cinder floating in the graveyard of the past. If the Earth survived the sun's expansion, it is now a frozen ball of rock orbiting a white dwarf in eternal darkness. You are looking at a tomb. This is the scientific idea that serves as the final reckoning of our journey, the reconciliation of our insignificance with our significance. As we stand on the edge of 1 trillion stars that have never heard our name, we are forced to confront the crushing scale of the cosmos. The observable universe stretches 93 billion light-years across, containing numbers of stars, sextillions, that the human mind simply cannot comprehend. On this map, a single human life is less than a microscopic spark that dies before it can even flicker in the dark. We are, quite literally, stardust that has gained consciousness, atoms forged in the hearts of ancient supernovae that have somehow organised themselves into a form capable of asking, why? The unsettling implication of this realisation is a profound sense of cosmic vertigo. We are small, yes, so small that the entire history of our species doesn't even qualify as a footnote in the biography of a single galaxy, and yet we are the only means by which the universe has come to know itself. Every time we solve an equation or look through a telescope, the cosmos is contemplating its own nature through our eyes. We are the eyes and minds of the universe, and that gives our lonely journey and weight that exceeds even the mass of our ship. We have carried the flame of awareness across a void that was never designed for us to cross. As you ponder this significance, you hear a sound you have never heard before. The amnesia clock has stopped. For eons, its obsidian hand moved only when a human civilization back on Earth collapsed. But now, the hand is motionless. This is the climax of our story, and its meaning is more terrifying than any silence of the void. The clock has not stopped because you have reached a final destination where time no longer matters. It has stopped because there is nothing left to record. Back home, in the millions of years you forfeited for your speed, the species that built this ship, the very lineage of Homo sapiens, has finally gone extinct. The blue marble is a silent, airless relic, and the civilizations that once debated the budgets of starships have vanished into the subduction zones of the Earth's crust. You are no longer an explorer. You are a temporal exile in the most absolute sense. You are a living fossil, a biological anomaly from a vanished epoch, carrying the DNA of a species that the universe has already forgotten. The beings who might now inhabit the galaxies you visit would be as different from you as you are from the primitive hominids who first stood upright on the African savannah. You are the last person from your now, a ghost haunting a future that shares only your physical coordinates but none of your history. This final isolation reveals the ultimate boundary of our reach. We have talked about the chemical wall and the Parker limit, but the real prison was always the era of isolation and the closing window of dark energy. Toby Ord identified that we are in a race against the very fabric of reality, an expansion that carries 3 entire galaxies beyond our reach every single year. Every second we waited to launch, an entire cosmic neighbourhood of billions of stars was incinerated by the growth of space itself. We are swimmers in an ocean where the water is being created in front of us faster than we can kick, and the horizon we see in our telescopes is a census of places we can never, ever go. As we look out at the trillion stars of Andromeda, we realise that the distance a human can travel in one lifetime is not a number found on a ruler. It is a negotiation with time. We can reach the nearest stars and return to a recognisable world. We can reach the heart of our galaxy and return to find our species transformed into something alien. Or we can leap between galaxies and accept that our journey is a one-way conversation with a future that will never reply. The equations permit almost anything, but they soften nothing. The universe has not built walls around us. It has built highways that stretch toward every horizon, highways we have not yet learned to travel, but that demand the total surrender of our origins as the toll for passage. We return to the silent, frozen face of the amnesia clock. Its purpose is fulfilled. It was designed to remind us that we are part of a larger story, even as we move beyond its pages. The stars are not mocking us with their distance. They are inviting us to become something greater than the biological containers that birthed us. They are the islands of the future, and we are the seeds of a new human lineage, planted in foreign soil and disconnected from the tree that produced us. The answer to how far we can go is ultimately not a limit of physics, but a limit of our own determination and sacrifice. We have found the key to the cosmos in the flexibility of time, but we are still learning how to turn it without breaking our own hearts. We are a species of flightless birds who have finally glimpsed the shoreline of another continent, realizing that to reach it, we must leave the island of our childhood behind forever. The stars are not unreachable. They merely demand a price we haven't yet learned how to pay. We are out here, watching the dark, because we understood that the horizon is only a boundary for those who refuse to move. We have traded our past for the infinite, and though the clock has stopped, our journey has only just begun.